Hey everyone, today we're going to be skipping ahead a little bit in the book, but kind of keeping an order of the AP format of the course, and that is taking a look at something called related rates. So this is going to utilize what we learned in our last video, which is implicit differentiation. So let's go ahead and begin. Now, a question that you might have asked thus far is, are there any practical applications of derivatives? All we've seen is just computing these problems without any real application. The answer is yes, and the first one that we're going to come to is something called related rates. Related rates are a concept that generally would spend maybe like a week, maybe a little bit more on. We're going to spend probably a couple of videos practicing these types of problems. Not nearly as in depth as I would like to go into them, but at least you'll get a foundation of what related rates are and should be able to solve these if you encounter them on the AP test. So let's go ahead and dive in. I'm going to start with actually just doing a problem. Then I'm going to go through and outline the sort of general guidelines of steps, how you'd want to solve these, because they're all different. There is kind of an order that you want to do these things, but every problem is different because these are word problems. So when you see related rates, think word problems. If you like word problems, great. If you don't, well, you're going to have to do a fair amount of them on the AP test anyhow, so learn to live with them. And they're at least a little bit more entertaining than just computing straight derivatives. So here we go with the first one. We've got Charlie and Billy. They share a beachside apartment together, and they decide to add some Christmas cheer by putting lights on their roof. Billy, he's atop a 10-foot ladder, and Charlie is standing 6 feet away. So up here is Billy, and down here is Charlie. Charlie is standing 6 feet away. He's providing moral support, but unfortunately he is not holding the ladder as he probably should be. And then unfortunately the ladder begins to fall. So the ladder starts to fall down. Down goes Billy. And as it starts to fall, the other part of the ladder is going to start to go out this way. And it actually hits Charlie because Charlie is standing there not paying attention. And so the ladder actually whacks Charlie as well. So both of them get injured in this catastrophe. So we are going to figure out at what rate of speed will the ladder collide with Charlie. All right, so let's begin with a framework here. We've already got a picture drawn. In a lot of these problems, you won't necessarily start with a picture, so you're going to need to draw your own little picture. I'm not very good at drawing, not a very good artist, but do the best that you can to sketch these situations. So I'm also just going to redraw this little triangle that we've got here. So we've got a triangle. The hypotenuse of the triangle represents the ladder. And this ladder is forming a right angle with the wall here. So I'm going to just put a little right angle box there. It's going to be important. You'll see this in a lot of situations. All right. And I'm going to go ahead and just maybe label some things. So when this thing is going to collide, this down here, I'm going to call this X. And that's going to be 6 when it collides, right? When it collides with Charlie. And then we'll call this Y. We don't know what Y is. Z is what we'll call our hypotenuse. Generally, you just call X, Y, and Z if you're labeling 3 sides of a right triangle. Z is always the hypotenuse. It doesn't really matter what you call the other 2 variables, but it's important that you call Z the hypotenuse, and that's going to be 10. All right, in addition, we have some extra. So what I've used here is we got a 10-foot ladder, so that's our Z. Charlie's standing 6 feet away, so that's where I got the bottom of my triangle, that leg. Now there's some other information. It says that the rate the ladder is falling is 4 feet per second. So it's going down this way at 4 feet per second. And what we want to figure out is the rate that this X is changing. So the rate that that's moving. What is the rate that that's moving there when it is at 6? So in this case, we're actually finding an instantaneous velocity, which is something that we've talked about throughout the course. They keep mentioning derivatives are instantaneous rates of change. So we want to know at what rate at one specific instant, what is the rate of change when the X, this distance here, is 6 feet. Eventually that ladder is going to keep sliding, and that would eventually be 10 feet, right, when the ladder is just then laying flat on the ground. it would be 10 feet, and then the speed would stop. But we want to know how fast is this ladder moving when it's 6 feet away from the wall when it collides with Charlie. So we're trying to find an instantaneous rate of speed. Now, where the name related rates comes from is, well, there's a rate that the ladder is moving down. We're going to call that dy dt. Dy dt. That represents the rate that y is changing. Then if we were to find another variable called dx dt, that would be the rate that x is changing. And both of these are with respect to time. So a little bit different than we've seen. We're differentiating these with respect to time. So that's why it's dy dt, dx dt, because it's the rate that something is changing with respect to time. And there actually is another one, since we have a third variable, that would be dz dt. And that would be, if we were to call variable that's the rate that z is changing. We're going to use these formats for variables as we move throughout these related rates problems. So anytime you see a d whatever variable, could be dA dt, dv dt, dr dt, these variables represent the rate that that variable is changing with respect to time. So in this particular problem, we're given the rate that y changes. So we know that dy dt is 4 feet per second. Now, when we write that, 4 feet per second, I want you to also think about if this is going to be a positive or a negative. Y is actually getting smaller as it moves down, right? Y is shrinking. So this is actually going to be a negative 4 feet per second because y is getting smaller. And what we're actually asked to find is dx dt. We want to find the speed that the x is changing, the x side there is changing. How fast is the bottom of the ladder moving out? So how fast is that gap changing? We're trying to solve for dx dt. It doesn't explicitly say it in the problem, but we actually know what dz dt is as well. Think about, this is a ladder, right? Assuming it's not a collapsible ladder, it looks like it's just a solid ladder. Assuming that ladder is just a solid ladder and it's not going to collapse, dz dt is actually going to be 0 because the ladder is just going to stay 10 feet as it falls down, right? I wish I could show you with my hands, but as this ladder falls down, it's actually not going to change at all. It's always going to be a 10-foot ladder. So that dz dt, that z side, is actually not going to change in any way. All right, so we've actually defined several variables here. We also have said that x is 6, right? Z is 10. Now, we don't know what y is, but there's a pretty easy way we could figure out y. And I want to go ahead and do that because in almost all of these problems, you're going to want to know what the y is as well. We do that just using the Pythagorean theorem. X squared plus y squared is z squared, or a squared plus b squared is c squared. You could call these x, y's, and z's. You could also call them a's, b's, and c's. It doesn't matter what you call your variables. So let's use Pythagorean theorem. It will be 6 squared plus y squared equals z squared. So that's 10 squared. And we're just going to solve for y. So we get y squared equals 100 minus 36 and the square root of that. So y is the square root of 64, which is 8. So now we know that as well. Y is 8. All right, now we're ready to get into the differentiation part of this problem. The first thing we need to do, whoops, I'm going to try to change colors here. The first thing that we need to do is figure out the formula that relates these rates. And it just so happens that the Pythagorean theorem is the formula we want to use that relates these rates in this case. X squared plus y squared equals z squared. So this is our formula. Now what we're going to do is differentiate this formula. Notice there's 3 variables. Each of these variables we're going to differentiate implicitly. If you remember implicit differentiation from the last video, whereas if we took like the derivative of y squared, we'd do 2y dy dx, or 2y dy dt. In this case, we're differentiating all of these with respect to t, time. So all of these are going to have that like y prime or x prime or z prime like we had in the last one. So how we're going to write each of these, the derivative of x squared is 2x dx dt. see that. Some textbooks might just say x prime, but it's a good idea to write dx dt because that shows you that you're differentiating with respect to time. So 2x dx dt plus 2y dy dt equals 2z dz dt. So anytime you differentiate a variable, you also have to throw a d, whatever variable that is, over dt next to it as well. All right. Now notice I did not plug in first. Did not plug in yet. And that is the reason why is I need to actually differentiate it before I plug it in. Because if I went ahead and just substituted in for x and y and z or whatever, then I wouldn't actually ever get to any of these rates. So I always have to differentiate first before I plug in any numbers into this formula. So after I've differentiated, now I can go ahead and plug in all the stuff that I know. So 2, I know x, it's 6. I don't know dx dt, but that's okay because that's what I'm trying to figure out. So after I'm done plugging in here, the only unknown variable I should have should be the one that I'm trying to figure out. Plus 2y, which was 8, dy dt, which is -4, plus 2 times z, which was 10, and dz dt is 0. So that's actually just going to make it go away because, again, the ladder doesn't change size. So dz dt will just be 0. All right, so that's the important step there. Now all I'm going to do is solve for my one unknown. Delete a little of this stuff here. So in solving for that, I got to exit this real quick. Sorry, when I change from my eraser, it makes me restart here. All right, so after I do that, I'm just going to solve here. So 2 times 6 is 12. So I have 12 dx dt plus 2 times 8 times -4, which is -64, equals 2 times 10 times 0 is just 0. So then I'm just going to solve for dx dt. So I get 12 dx dt equals, add the 64 over, and then just divide by 12. So dx dt equals, and it's okay to go ahead and write this as a decimal. On the AP test, for rounding, you always want to keep 3 decimal places unless it says otherwise. 3 decimals. And you can round to the 3rd decimal place unless it says otherwise. So when we do 64 divided by 12, that's 5.333. And also we need to make sure we have the correct unit. You would maybe see this on one of the free response questions. The correct unit here is going to be feet per second. So that ladder is going to hit Charlie at 5.33 feet per second. That's how fast the ladder is going to be moving. So I suppose if you wanted to, knowing that you know the velocity, you could figure out what the weight of the ladder, how hard this thing is going to hit Charlie, figure out how badly he's going to be hurt. It's definitely going to be moving at a pretty good clip there. It's going to have a sore leg the next morning, that's for sure. All right, so that is how you solve a related rates problem. Now, all of these are a little bit different. They all keep this general strategy here. And I don't expect you to have a great idea of what's going on right now. These take a lot of practice. So I'm going to give you an outline of sort of what I did, and then we'll look at maybe 2 more problems. So here's just a general strategy. The first thing that you always want to do is draw a picture. If it gives you a picture, great. If it doesn't, definitely draw a picture. And even if it gives you a picture, I generally like to draw my own little picture as well. Second step, identify whatever formulas are associated with the problem. So on that last one, I wouldn't use the Pythagorean theorem. Generally, if you have a right triangle, Pythagorean theorem is going to be what you're going to do. Unless you're talking about angles, then angles, you're going to be using some trig formulas. Next, we want to identify whatever info is given, and we want to label this on our diagram. I suppose you could switch 2 and 3. It doesn't really matter what order those go in. But identify all the info that's given. Try to give it an appropriate label. So if it's x, give it an x. If it's a rate of change, so if it says it's changing at this rate or shrinking or growing or moving, you should always have a d, whatever variable, over dt. So that should always have a d with a dt if it's changing. Identify what the unknown variable is. So what are you trying to figure out? Are you trying to figure out dy dt? Are you trying to figure out dA dt? What variable are you supposed to try to figure out? It's pretty much always going to be a rate of change. So always, well, in most cases, be the d whatever dt. Now, sometimes we'll have to do like a little intermediate calculation before we get to the related rates calculation. Like on this previous problem, I actually had to do a little side problem here to figure out what y was. And it's okay if you don't even do that right away. Maybe you get to this point of the problem here where you're plugging in and you realize, oh, I have two unknown variables, so I need to go back and figure out what y is. So then you go back and you do this. I have just done a lot of these problems, so I kind of already knew we're going to have to do that y. But you might get to a point in the problem after you've differentiated, you realize you have more than one unknown variable, so you got to figure out a different way to find the other unknown variable so you can solve your problem. Next, you're going to implicitly differentiate. Notice you're going to do that before you plug in. You're going to implicitly differentiate, so that means you're always going to have like a dx dt or dy dt, dA dt, whatever, after you differentiate, or dr dt, always with respect to t. So always got to put the d whatever dt next to it. Then you can plug in all your given variables. And then at that point, you can solve for your unknown variables. And again, if you have more than one unknown, you might need to somehow do another calculation to figure out what the other unknown was and then finish the problem from there. That's a very basic outline. Each problem is different, but just in general, these are the things that you need to do. So let's go ahead and with that look at a different problem. So in this one, we've got a thin sheet of ice, and this ice is in the form of a circle. So I'm going to just draw a little picture here. Thin sheet of ice in the form of a circle. If the ice is melting away, so this is shrinking because we're warming up outside maybe, such a way that the area of the sheet is decreasing at a rate of 0.5 meters per second squared. At what rate is the radius decreasing when the area of the sheet is 12 meters squared? All right, so you can see we're talking about two rates. That's why it's called a related rate. We know one rate, we got to figure out another rate. So somehow these are related to each other. So you can think to yourself, how are these rates related? It's a good question to ask, right? Because it's called a related rate. In other words, what formula can we use to relate these two rates? Well, let's go ahead and just label what we've got. Maybe that'll help. It says that the area is decreasing. So if we're talking about area, the variable I want to use is A. So I'm going to say dA dt. That represents the rate that the area is changing. dA dt. Rate area is changing with respect to time. That's what dA dt. So that is 0.5 meters squared per second. Right. We want to figure out what is the rate of the radius decreasing. So at what rate is the radius decreasing? Well, so we want to find dr dt. What rate is the radius decreasing? What is that? Now, we're not given a lot of other information. So we need to figure out a formula that's going to work. I'm going to draw a little radius here. It doesn't even tell us what the radius is in this formula. It just gives us one rate, and we're supposed to figure out another rate. But there is a way we can relate these two. So think about what's a formula that has A and an R in it that relates to circles. Well, obviously, that formula is going to be area. Area for a circle is pi r squared. Hopefully you know that. If not, you need to know that. So that's our formula we want to use. All right, so let's go ahead and just go ahead and differentiate this. We might be missing something, but let's go ahead and differentiate this and see maybe what we're missing. Remember, you don't want to plug anything in before you differentiate. And honestly, there's no place you could actually plug anything in at this point because we're just have a rate of change, and that doesn't even appear in this until we differentiate it. So to differentiate this, the derivative of a, well, just think of it like the derivative of x, which is like the first power. So the derivative of a would just be 1, but we have to always slap on the dA dt. So the derivative of a is just dA dt. That's the implicit derivative. Now with this pi r squared, remember pi is just a constant. So it's no different than 3r squared. This just happens to be 3.14159, whatever after that. It's just a constant r squared. So we do the same method. We bring the 2 down in front and multiply. So we're just going to write this as 2 pi r, and now it's the first power because we subtract 1. And then since we took the derivative of a variable, we also got to write dr dt after that. So this is our implicit differentiation right there. Now notice this is good because we've got a dA dt, which we know, and a dr dt, which we want to know. So that's great because we figured out how to relate those two variables. The only problem is if we go to start substituting here, plug in what we know dA dt is 0.5 equals 2 pi. We don't know what r is. And that's a problem because we can't have two unknown variables. We need to figure out dr dt, but if we don't know what r is, we can't solve that. So we need to figure out what r is in some other way. Well, there is a way we can do that. It does say that the area of the sheet is 12 meters squared. So at some point, the area is 12 meters squared. Now that a went away. Again, we didn't actually want to plug it in there initially. I probably should have written it out initially, but at any rate, we didn't want to plug it in there to begin with anyhow because we need to always differentiate first before we plug that in. So it does tell us that the a is 12, but there's not even any place to plug it into this formula. Well, we do need that information, and that is because we got to use it to figure out r. So if we use the same formula of a equals pi r squared, we can, again, this is just sort of a side calculation. We can use the fact that we're figuring out this rate of change at the instant that the a is 12. So I'm just going to go ahead and plug it in here. A is 12 pi r squared. I don't need to differentiate this at all. I'm just trying to figure out what r is when the a is 12. So if I were to solve this, divide by pi, then take the square root. So r is the square root of 12 over pi. I wouldn't write this as a decimal yet. On the AP test, you don't want to have any intermediate decimals. You just want to round the decimal at the very end. So I wouldn't even compute this as a decimal yet. I would just leave it as this and plug it into your problem here. So where r was, I'm just going to plug in square root of 12 over pi. Like that. So now we know everything except dr dt. So that's great. To solve for dr dt, all I have to do is divide 0.5 by all the stuff that are attached to dr dt because this is all a constant. So divide by 2 pi times the square root of 12 over pi. And there's both inside the square root. And that equals dr dt. One other thing I should mention as well, sometimes I personally forget to catch this till the end. Think about if something is decreasing, that should be negative. So I should have made this dA dt a negative. What just made me think of it is I know my answer should be negative because I know my radius is decreasing. So I remember that my answer should be negative, so there should be a negative with that dA dt. All right. So when I type in my answer, it's going to be 0.5, negative 0.5. Just type it all in as is. Don't try to round or anything to the very end. Divided by that whole thing in parentheses there, 2 pi times the square root of 12 over pi. And we should get negative 0.040. I'll write it out here. Negative 0.0407. The AP test generally wants you to round the third decimal, so this would round up to negative 0.041, and we need to make sure we have the correct units here. And the correct unit would be meters squared per second. Sorry, it should be meters per second, not meters squared. One thing to remember is area is always units squared. Volume is always units cubed. So the reason that my area here, rate of change, was meters squared is because you're multiplying sort of two units together. It's always being units squared, but radius is just a single unit. So it should just be meters per second. Just change it at a meter per second. But an area would change at a meter squared per second. All right. Again, I know these are not easy. They take a lot of practice, and there's a lot of different situations. So let's go ahead and do one more. All right. For this one, we've got a plane that is flying 750 meters in the air, flying parallel to the ground at a speed of 100 meters per second. And it's initially 2.5 kilometers away from a radar station. That's on the ground, 2.5 kilometers. So the question is, at what rate is the distance between the plane and the radar station changing? And this question, I think, is missing a few extra words that would be helpful. And that is that the plane is actually flying towards the radar station. So I'm going to draw this one. Here's my little radar station on the ground. I got my plane up here. Told you I was bad at drawing. So you got a plane up here. It's flying this way. It's flying across the sky, right? Flying this way. And kind of filling in the gaps here. It says that it's flying parallel to the ground. So that should be a straight line if the ground's here. Flying parallel to the ground at 100 meters per second. So it's moving this way at 100 meters per second. We know that this plane is 750 meters in the air. So this distance is 750 meters. And it also says that the plane is 2.5 kilometers away from the radar station. That's talking about distance on the ground. So this is 2.5 kilometers. One thing to notice, they changed units on you here. So I'm going to go ahead and just convert this to meters. Remember, kilometers, you have to move it to, 3 decimal places. So 2.5 kilometers would be 1, 2, 3 meters. So this would be 2,500 meters. 2.5 kilometers. Move it 3 places. All right, so this is 2,500 meters. And we're asked to find what rate is the distance between these changing. So the distance measure would be from this radar station to the plane. How fast is that changing? So we probably want to go ahead and give these some labels. Let's stick with, since we have a triangle formed here, let's stick with the same variables we used for the other one. This would form a right triangle, right? The ground there, because it's flying parallel. So let's just call this X, Y, and Z again. So we know X, we know Y. We don't know Z, so we'll probably need to figure that out. Since this is moving at 100 meters per second parallel, it's actually equivalent to the speed that this is going to be decreasing. This X down here is going to be decreasing. So the variables that we actually know, we know X is 2,500. We know Y, 750. We actually know dx dt, because dx dt, again, this would be 100 meters per second, would tell us the rate that that X is sort of shrinking. So dx dt is negative 100 meters per second, because it's shrinking. Dy dt, whoopsies. Now the plane is flying parallel, so that dy dt shouldn't be changing. He's staying 750 meters above the ground, so that's actually going to be 0. Z, we don't know yet. We could figure that out pretty easily though. Dz dt, we don't know, but that's what we want to figure out. At what rate is that changing? So we'd want to use our same formula to relate the rates. That's what we're going to think. How can I relate these rates of change? we would only use our Pythagorean theorem, x squared plus y squared equals z squared. And let's go ahead and just do our implicit derivative. So we get 2x dx dt. It's going to be exactly the same as when we implicitly differentiated this before, plus 2y dy dt equals 2z dz dt. And if we start to do some plugging in here, you'll see we need one other variable. So we got 2 times 2,500. Dx dt is negative 100 plus 2y is 750. dy dt is 0, so that's all going to go away, equals 2. Now we don't know z or dz dt. We need to find dz dt, so we need to, before we do that, we need to figure out what z is. To do that, we just use the Pythagorean theorem. So we're going to just use it again, except this time we don't differentiate it. We just use the fact that we know x and we know y, which means we can figure out z. So we do 2,500 squared plus 750 squared equals z squared. So when solving that, z then is just going to be the square root of those two. And honestly, you're probably best just leaving it like this. I know it's kind of a pain to write it, but that way you don't lose any decimal places. So if you just plug it in this way here, square root of this, I'm just going to scribble that for now, and then dz dt. So that when you solve this, you're not losing decimal places as you go. When you solve this, suppose this part you could figure out pretty easily. This is just going to be, when you do the 2 times 2,500, give you 5,000 times negative 100 would be negative, and then 1, 2 zeros, I believe that should be good. This all just goes to 0 equals, and then I'm just going to keep this 2 times the square root of 2,500 squared plus 750 squared dz dt. And then we're just going to need to divide on both sides. It is important on the AP test that you're showing your work. They will not give you credit if you do not show your work. So it is important that you do that. As monotonous as it might seem sometimes, do it so you can get full credit. All right, and I'm just going to type that whole thing into my calculator. Negative 500,000 divided by 2 square root of 2,500 squared plus 750 squared. And magic number, negative 95.7826, so 0.783. We also need to make sure we're doing our units here. Think about what variable we did. We did z, and this was in meters per second, so that is going to be changing in meters per second as well. So that means the distance between that plane and the radar tower are changing at a rate of negative 95 meters per second approximately. Throw it on there. All right. So that's another example. There's 3 of them. All of these do take a substantial amount of time. Again, this would be about a week-long thing we would be doing these types of problems. We'll probably do a couple different videos here. I want you to try your best on these problems. Feel free to let me know if you want to meet sometime in person on Thursday or Friday when you guys are here. But again, do your best. Make sure you're following these steps. I can also post some other videos possibly of related rates if you want extra practice. Just do your best again. I know this is difficult. It's especially difficult to teach this in an online format. However, I want you to do your best, and again, reach out to me if you need help. Thanks. Bye.